Okay, as we get going, let's go ahead and answer a question for the folks who are watching on video too. The question came up about really, why is that custom node showing up in gray? You know, why is it happening that way as opposed to all these nodes that are showing up in gold and look very, very happy right now? What is the story with that one? And as best I can tell, the nodes which are serving as functions which aren't fully resolved because this node really doesn't have a value because value to test isn't actually filled in yet until the looping actually takes place. Because it doesn't actually resolve to a value, you can't preview it, it doesn't show as resolved. It's kind of like just an open placeholder. These other ones, you know, they will go ahead and return some sort of result, but this one, it just doesn't. It's just known as a function. So it's just waiting to be plugged in. So it kind of shows up that way for you now. And let's test it. I think that'll actually be true as we keep on going with some other ones. Okay, if you have that worked out and you can handle looping through all these different values, let's go ahead and kind of take a look at the other idea of recursion. And I won't deep end on that because it's just sort of another way of doing it, but it actually is a very useful way of doing it. And I want you to sort of be exposed to that as an alternate way of going and thinking out looping, because I think it's actually more powerful in a lot of instances. Here's the deal. As we were doing for each, we created a range of values to test. We created this custom node. We basically performed where we went through, wrote the first line of the file, we evaluated each of those different values to test, and we read the file at the tail end. So that was our basic loop in terms of setting things up. For the next example, example 11.3, we'll do the same thing, but do it using recursion. And I'm just going to tell you what the difference is. It's really, I've highlighted it in terms of red here, in terms of where things are going to be different. Setting up the inputs is going to be almost exactly the same. Same input parameters for almost everything. For the highest value, though, I want you to think of it not just as sort of the maximum value that the height can be. It could be some other stop criteria. It could be that the daylighting value is less than 40-foot candles. It could have been any sort of criteria that you want to put in there. It doesn't necessarily have to be related to the initial value in the increment. Okay, it's really just some value that you're going to test against. You're going to test your results against to say, you know, are the results below or above some threshold that we're interested in? So it's really whatever the threshold is. That's going to be the cutoff threshold. So, you know, I guess that's another good way to express that. Is really, it could be the stop criteria, or it could be just kind of what I'll call the cutoff threshold. But basically, we're going to put an if in place, and based on some value that's coming out of the model, if it crosses that threshold, we'll know it's time to stop. Yes? Oh, no, that is quite fine. In fact, that's what we'll do next in terms of saying we want to do multiple variables. So that's good because, you know, we're traversing down a single variable to test. Exactly. We could be testing two and then saying, great, you know, really whichever one of these is true or whichever one is worse. No, exactly. So it could be stopping based on two different values. We can put as many different thresholds in here as possible as we need, and then construct an if that says if any of these conditions is true. So if the cost is greater than this, or the daylighting value is greater than this, or the energy use is greater than this, and if any of those things are true or false, you know, stop based on that. So it can be a compound criteria. That's a good way. No, exactly. That's a very good way of thinking about it. Highest value. So could be many thresholds. No harm, because all we're going to do is put together an if statement. And as soon as that if statement becomes true or false, then we'll know it's time to stop. Very good. Okay. The next step was create the range of values to test. That's the one, wipe that out. We're not going to create a range of values to test. Okay, because we don't do that anymore. Okay, now we're going to do it through recursion instead. Okay, we're going to create this custom node to test the values. It's going to be just like the old node. Not a whole lot of change to it, except after we set the element parameter and then get the element parameter and compute the results, we're going to decide whether or not to keep on going. Okay, and this is going to be, we'll have some sort of formula that really looks at this criteria and whether we will continue. So whatever it is, if we want to get that daylighting value and multiply it by 5 or whatever it is, we're going to somehow compute the evaluation criteria. We're going to figure out how does that compare to the stop condition, or maybe multiple stop conditions. And then it's going to be, if true, go ahead and, no, you know, actually even true or false really depends on how you've written the logic. The way I've written it is, if true, keep on going. If false, stop. Okay, so it could be a complex series in here, but if true, and keep on going basically means, you know, call the same function again. So it's going to sound weird. We're just going to basically keep calling ourselves. So, and every time we call ourselves, we're just going to swap in the new value to test. So it's going to, sounds kind of strange, but it just kind of keeps on slipping things in under the door in terms of that input value. Just keeps on changing it on the fly. And when it's false, it says, don't do anything. But maybe that'll be easier to see in the context, in the real context, as opposed to in the abstract. It sounds kind of strange and obtuse, but maybe it'll make more sense. Okay, I can work with that same model file. There's really no difference between 11.2 and 11.3 there. So let's go ahead and, excuse me, let's open up Dynamo. And we'll open up the slightly different scripting file. So we'll say, here's Dynamo. We'll go to, where'd it go? Not in the core. .11.3. Okay, again, I'm going to have a slightly different node here called get volume values recursive. It's going to look amazingly like the old one, set up a little bit different on the input and has this if statement in it. Let's take a look at it. So most of this will look very much the same. I'm still writing that string. I got the big perform to kind of make everything happen. That's all the same. Here I'm still just using the notion of a highest value to test, but this could get sort of much more interesting. This could be some sort of stop threshold, and we could use a formula, kind of comparing the results to that stop threshold. It doesn't have to be highest value to test, but I kept it kind of very parallel. I should talk about how to do that a little bit differently. But here's what we're going to do. What we're going to go through and do is, as opposed to computing a whole range of values to test, we're going to say, okay, get yourself started by passing in the initial value to test. Okay, and based on that initial value, we're also going to pass in the increment. That's how far to go to compute the next value if you are going to compute a next value, and the threshold, the highest value, you know, that you really want to stop against. Okay, and within that, let me go ahead and open this up and show you what this node looks like. I think even here, it probably makes more sense. I'm going to change the name of this input to stop threshold. I think that's an easier way for me to think about it. Okay. But what we're going to do is, at the upper end of this, it's going to look just the same. I'm going to set the element parameter. I'm going to get the element parameter. I'm going to go through, and for that element parameter, I'm going to go through and multiply it by the scaling factor and write it out. That part didn't change at all. For what I do for any individual line, it really looks just the same. Write the CSV value, concatenate the strings, write it out. So what I did on this individual line, this individual test, no difference. Where it gets interesting, though, is how you basically get it to do the next thing. And how that happens is we have a perform function. The perform used to have 3 steps, which was, you know, basically set the value, get the value, then write the file. The 4th step here is actually go ahead and figure out if you need to launch another test. Okay, so that's what the fourth step is here, and let's take a look at how it's constructed. I have a pretty simple test here. My test is just really, since I was testing just have you cross some threshold in terms of distance from where I wanted to go. Yeah, all I'm doing is saying, let me get the prior value, that was the initial value I came in with, add the increment to it. And then what I'm doing is just comparing, yeah, is that less than or equal to the cutoff value? So I got my stop threshold. It's basically, is the next proposed value, and you can kind of rename that. That's just really the potential next value. In this case, I'm just adding to it. Okay, this guy over here is really testing, is it less than or equal to the threshold? Okay, if it is less than or equal to the stop threshold, basically send the same function out, but instead of going through and sending it out with the old value to test, we're going to give it the new value to test, the potential value that has that increment added to it. Okay, if false, do nothing. Okay, so that's how it knows how to stop. So when you finally cross the threshold, it'll do nothing. So at that point, it all just rolls back and all the values are reported out. So let's take and see if we can like dwell on this for just a second, because I think it relates to your question. It's a really good question. It's this whole notion of this next value to test and what could it be, because this if-then logic could be really quite interesting. And even the potential next value to test doesn't have to just be plus increment. We could be changing the increment. We could, deciding really what the next value to test is, again, something we can compute based on sort of what we're trying to test. So maybe early on our increment's 10, but we could say that, over here, if the difference between the computed value and some sort of threshold is less than 10, that we go for a much smaller increment. So we get very fine testing when we get close to the point versus very gross post testing as we're narrowing in. Yeah, it could be these compound ifs where we have several different things we're computing, and then the if is really some combination of all those different things added together. But at the tail end, you want all your criteria to add together and have a combined either yes, go, or don't go. And then if you are going, just send it the next value on down. So where this gets to be so useful is if on the, it's different cases. It is the complex criteria that you may have 4 or 5 different criteria and any one of them might trigger the problem. Or if you have 4 or 5 different criteria and based on those criteria, the next value you test might not just be sort of a simple linear thing, but you want to sort of change the value that you're testing based on some sense of how close or the direction you want to be heading in. Okay, so where that's really useful is, for example, if you have a very big space to traverse, if you have 1,000 points by 1,000 points, evaluating all those points may be very, very time consuming, whereas this sort of strategy lets you say, hey, let's just go ahead and I'll go over every 20 points and every 20 points, and only when it starts getting to be interesting will I get down to every 5 points or down to every 1 point. But by using this sort of a strategy and programmatically figuring out the next thing to test as opposed to just doing it by brute force, you can really hone in on the thing that you want much more efficiently. Okay, so that's just kind of an overall principle of optimization that really, especially when we start doing big multidimensional optimizations and we're doing something like computing daylighting values or something like that, every computation might take several minutes. So as opposed to having 1,000 computations, if we can get to the answer in 20 computations, that's really going to be much better for us. So it's really all about trying to optimize how we move through the whole search space. Make sense? Okay, leave it there as a principle for now. We will test this as we keep on going. But as a principle, leave it there. And let's just try running this thing to sort of get the same sense of what's going on. At some level, it looks just the same in terms of what's going on. I have 20. I'm going to go up to 40 or 50, whatever it is that I'm interested in doing. Kind of just shove it over there. See if I can get that out of the way. But when you run it, okay, it's basically going to do the same thing. It doesn't look a whole lot different than it did before because really the results that it's returning are just very much the same. It's really just the whole strategy of how we move through the search space. So it's returning the same basic thing. So that's all I want to give you in terms of recursion versus non-recursion. For each loops or sort of brute force, recursion gives you a little more control about, dynamically changing your search strategy as you go. Okay, so let's leave it at that. Okay, to wrap us up today, let's take it to the next logical step. And that is to say, great, okay, we've computed all these values, either using brute force or using recursion. That sounds pretty good. But what if I actually want to get to something? I want to get to the maximum or I want to get to the minimum of something that I don't just want to get a list of values. I actually want to sort of figure out what the highest or the lowest value is. Okay, and let's show you how that works. In terms of doing that, we're going to do something very similar to what we did before. We've produced this fantastic list of all these different values. For every value of the height, we first return the gross volume. But what we're going to do is actually take that list and go a little bit further. We're going to say, great, you've given us a list of all these different things. Can I convert that back to a list of values that I can operate on? So it's just a bunch of text. Can I convert that into a bunch of values? And what we've done is actually put together a node that just really takes text that's formatted in the comma-separated value scheme, and it's going to break it into a series of hierarchical lists. So it'll be a bunch of rows where every row is going to have the test value and then have the result value. Okay. After that, we're going to go through and just try to get those result values. We can say, hey, great. You got a list of values out there. Give me every second node in that list. So in every row, give me the second value. That would give me all the results values. So we can do that. The third thing we might try to do is let's find the extreme, either the max or the min in any of those columns. Okay? And then we can actually report the max and the min out. And the final thing would be say, hey, great, given that we can get a max or a min, can we actually set the Revit model to be that max or the min? So based on whatever the calculation came up with, can you set it to actually give you that max or the min? That sort of make sense? Okay, let me do this. I was going to show you example 11.3. Okay. Well, let me show you that first. And then I'll go to 11.4, then I'll take you to 11.5 real quickly. In 11.3, go over to, or 4, excuse me. Let's open up 11.4. Okay, this is going to find the max or min just based on these gross volume values. And you'll see, I have the same sort of things, some of the older formulas before. I have a couple new things in here, like converting a CSV into this hierarchical list, or getting the extreme values, or getting a result column. Let's just take a look at some of those. Okay. So as we look at the whole left-hand side of this diagram, you can see it's just the same as it was before. I got this looping going on. I got this writing of a file going on. I got the perform all going on. Up to that, the left-hand side is pretty much what we've seen before. Okay. Now we're going to go ahead and take it one step further. Let me just go ahead and run this so I can have some values for you to look at. Not that. Okay, it's doing some calculation in the background. I think it's done. Okay, so it's gone through and it's computed some values here. Everywhere 20 to 95, it's given us all those different values. What we want to do now is take that big string of text and just break it down into a series of data values that we can use. So here's what we're going to do. We're going to run it through some function we've written called take that text string and break it into hierarchical lists. Let me show you what that's like. Let me try just the tail end of that. I'll put a watch in here so you can see what it did. What that's doing is it's just taking all those values and just putting them back into lists of values. And I like lists of values because I know how to operate on lists of values in terms of finding different things. So each of these different rows, the initial lists, are just the pairs of the test value and the result value. And then 0 and 1, column 0 is the test value, column 1 is the result value. And if I had 2 or 3 different things I was computing, I could have, value 2 and 3 and 4 for each of those different rows too. Okay, so that's all this function does. In terms of this function, it's kind of a nice function. Go ahead and take a look at it. I won't break it down too much right now, but it basically takes, just an input string, and we sort of evaluate whether you say that the first row is a header string that we want to strip off, just like the report header, or not. And based upon whether it is, it just goes through and row by row, just breaks it up by first carriage returns. So it splits the string based on carriage returns, and then it splits it based on commas. And out of that, it's basically going through and just returning a whole bunch of values, lists within lists. But again, I don't want to get into that right now. I just want to show you sort of what it does. Maybe we'll talk about it some more next time in terms of how that function is defined. After we've broken into the list, what I'd love to do is say, hey, I've got a list. Can I go through and actually get the different column values? Can I sort of get all the values from column 0? Can I get all the column values from column 1? Okay. So again, we set up a little function to do that. If I edit that node, I'm basically just saying, take a list of values and the number of the column you want to get, and then there's a function called getFromList, where if I go through and say that for every item in the list, I want to get from list things at the column number, it'll evaluate that for each different item in the list and get all those different items. So this is an example of, this is called mapping. So mapping is very much like performing all. What mapping does is it just takes this function, getFromList, okay, and it maps it across the entire list and basically returns the value for what the function would be for all those different elements in the list. So let me show you what it does. Come back over here. So if I want to go through and get everything from the column to get 0, it gives me the list of values at column 0. If I also say, let's go ahead and get all the values from column 1, it'll get all the values from column 1. Okay. The last function, and we'll take a look at this in more detail next time, is really a function we put together to just sort of get the extreme values. So let's talk about that. What I want to do is I want to take these 2 different lists, and what I'm trying to do is really figure out, okay, given these 2 different lists, where is the extreme value, either the extreme high or the extreme low value on this list? And based on where that is, if it's position 7, I want to basically get the test value and the output value, that is the extreme high. If I want to get the extreme low, I want to get the test value and the output value for the extreme low. And how we can do that is, again, I set these up as little custom nodes only in that they're sort of very easily reusable that way. So let me show you how this one works, and we'll again debug this in some more detail next time. we're going to say take a hierarchical list and a column number. So column 1 would basically return the test values for the first test, as opposed to 0 being the values that we tested. Get that value from the list. Okay, map it. That's just going through and returning those values. And then what I'm doing is just basically sorting the list by that value. So I'm sorting by the column 1 values. I can sort of say, great, grab the first item in the list and grab the last item in the list. That'll give me the highest and the lowest based on that returned value. And then from that, I can say, great, once you've told me what the first list is, I can get the first element, which will be the input, the second element, which will be the result. Again, the first element, which will be for the max, the input, the second element, which will be the result. So what that's doing is back over here, I got this nice list. I'm sorting it based on the values in column 1, and then as I'm going through and finding out that element 0 is the low and element 5 is the high, I'm grabbing the first and the second just to get the high and low values and reporting those back. Okay, and just reporting those as a bunch of data values out. And finally setting the element parameter. Let's go ahead, we'll debug this more next time, but let's go ahead and actually show you how it can work in a way that's a little more interesting. And to do that, just as you're leaving, let's go ahead and open, if you can, just to sort of see how this basic logic is more useful. Go ahead and open up, if you can, session 11, the example that's 11.5. And we'll talk about this. This is sort of a box that I set up that has just a little bit more interesting value to it. This is a box where in the parameter values, and we'll show you how we did it next time, I've basically got it set so that for any height that we put in, it's going to go through and compute a width and a depth that'll always try to give the same amount of target floor area in the building. Okay, so I have a parameter for the target floor area. It looks like it's about 100,000 square feet. So for any height in the building, it'll figure out what the length and the width, or the width and the depth of the building would have to be to give you that floor area. Okay, based on an assumption about the floor-to-floor height. Okay, so for 100,000, if the floor-to-floor height were 10, I'd need about 100 by 100 building. If it was 12, I'd need about 112 by 112. If it was 15, I need a building that's about close to 130 feet by 130. So it's a formula that just sort of is mapped in there. It has a sort of complex relationship between the total target area, the floor-to-floor height, and ultimately I'm just doing a square root to break it so that the height and the width, or the width and the depth are the same. Okay, but let's, independent of all that logic, just show you how the optimization works relative to this. Say add-ins, open it up, and I want to give you this just so you can sort of play with it between now and next time. Go to session 11, 11.5, open that example. Okay, this is actually just like the one that we set up before. It's just set up a little bit differently in terms of letting us put any value in there. What I'm going to do is actually try testing the height against the gross surface area. I always have this thing about trying to figure out what is the best shape relative to the surface area on the building, because the surface area of the building actually has the most impact on the energy use. Okay, of course, we should probably subtract out the floor or the base, but that's okay. We'll leave it at this for now. So the idea is, can we go through and change the height of the building anywhere from, say, 20 feet to 200 feet, run this and just go through and compute the different surface areas and figure out what's the best shape for the minimum surface area, what's the worst shape for the maximum surface area. Okay, let's go ahead and run it. And you can see it's going through a lot of variations back in there, changing the shape of the building, computing all that stuff. Okay, let's take a look and see what it did. So the values that got returned are for each of the different potential heights of the building. You see that we have everything from 225 all the way down to 79, 84, 78. That's kind of interesting. There's actually a little bit of, there's almost like two lows within there. It's kind of interesting about why 90 and 120 actually worked out to be pretty similar, and we'd have to kind of think about the geometry and why that is. But clearly, the very low, squatty 20-foot building is the worst surface area. Somewhere around 100 to 120, 190 actually worked out to be pretty good. Okay, what we're doing is, after we get those values, just going through and computing what the high and low is, pulling them out of those values. You can see that what it's decided is the absolute best is 120. That's the minimum value. The maximum value is 225, 298. That's at the test value of 20. Okay, and what's happening is out of that, we're basically setting the value of the building over here to be 120 by 111 by 111. Okay, in terms of thinking about the logic of this, and it's what we talk about sometimes in the building performance class, it ultimately turns out that buildings that are very cubic in form or as close to spherical as possible tend to be the best performers in terms of just the mathematical relationship between the amount of volume you can enclose in the surface area. So it's not surprising that in this case, the relatively cubic building actually gives us the least surface area. The one that's very squatty gives us a very bad surface area. So whatever. That just kind of confirms that result. But it's interesting because now we talk about that kind of conceptually, why the closer you can be to a sphere, the better. But even if we started going through and playing this, we can get a similar result. But an interesting thing we could do now would be, let's go a little bit further and say, if we, for example, associated different costs or different U values with those different surfaces, we could say not just the surface area, but we could say, let's evaluate it based on the predicted energy loss through the different surfaces and actually get a more refined value and optimize based on that. So that would be our next step. We could, for example, assign a U value to the roof and a U value to the different wall surfaces, and then really based on finding the best value of, or the minimum value for the energy uses for all those different surfaces, you come up with a different value. Maybe we'll do that next time. Okay, let us break for today. Let's get you out of here, and the TAs and I are going to write up your assignment and get that out to you so you can hopefully get a chance to play around with it. Okay, very good. Okay, excellent. Okay, thank you.